clearing doubts. So I will sort of let you ask the questions, and we'll proceed that way. All right. So start off. So if you want to ask questions on the chat, that's fine. You can also ask questions by unmuting and asking your questions. Go ahead. Are there really no questions? You can also say anything, any of the lectures which you don't understand, and then we can sort of see what we can unpick that, and then see what is missing, right? So we can also try to do that. Okay. Okay. Really good. So I'm happy that there was at least one question. So Satak, thank you for asking this question. So Satak has a question which says, are arrays mutable? How are they implemented? So arrays are mutable. So they are implemented the same way that you implement arrays in C, right? So what are arrays? Arrays are these structures that give you collection of cells that you can index it efficiently, right? So they allow you random access, but the important bit is the cost of accessing any array element is constant time, right? So, and the way we achieve this constant time is every array has in C, right? In C, every array has a location where it is allocated, and then you have all of the array elements laid out in contiguous memory sequence, right? So the first element is at index 0, and that is the start of the array, and the second element is at index 1, and that is the array start plus the size of the address of that second element is the start of the array plus the size of the first element, right? And the second element is array start plus twice the size of the array element, right? So that you can efficiently index into anywhere in the array just by doing this computation. If you want to access the nth element, you just take n-1 sizes of the array elements, and then that's the position at which you access it. In OCaml, they are laid out the exact same way, right? So you have C arrays, you have your OCaml arrays are laid out exactly the same way. They are in fact mutable. You can manipulate the arrays in the same way. So there are a little bit they are laid out the same way, but there is a little bit of metadata associated with arrays. In particular, you need to know the size of the array, right? Whenever you access arrays in C, you don't do array bounds check. So you can access anywhere in the, you can index it with any number, and C will try to access that memory. But in OCaml, we have type safety. So what OCaml arrays will do is they need to access the size of the array and then make sure that the index is within the size, right? So there is some metadata that is sitting somewhere, and yeah, so every object in OCaml has this idea of a header. So there is one word associated with every object in OCaml on the heap, and that is where the metadata is, and arrays also have the metadata. Modulo this metadata, array layout is the same as C. So they give you constant time random access, and they are not growable, just like C. Does that answer your question, Sarthak?
Sir?
Yeah.
Sir, I had a doubt regarding constructors.
Okay.
So like, how do we implement, like, what is the sense of constructors for OCaml? Like when we are doing some types, right? Like
Mm-hmm.
like the base case is just a constructor. Like it's not
Yeah,
of some int or something. So
yeah.
like, what does it mean to the OCaml compiler? How does it like implement this, like for pattern matching and all? Like how does it
Okay.
make sense of this thing?
So so there are two questions here, right? So firstly, let's make sure that the easy one is answered. So you so there is no question about how to use the constructors, right? So is that right, Venkat?
Yes, sir. Like the usage is fine. I just want
Okay.
to know what does it mean? Like how the compiler interprets our usage of constructors.
Yeah. So there is an interesting part of OCaml which we are not covering. So in particular, OCaml has a memory representation of all of the things that you write. Right? If I write a program which has constructors, OCaml has to somehow translate that to memory. And a beautiful thing about OCaml is it has a uniform memory representation. What this means is every value in OCaml, be it constructors, be it integers, floating points, or etc., they're all of the same size. They're of size one word, right? And when you have, say, what is a good example? Say, let's take a list, right? When you take a list which has a nil constructor and a cons constructor, right? Nil constructor is actually represented by on a 64-bit machine, a 64-bit value, right? It will just be value 0 or value 1. I don't remember the exact number, but it's just a value. It's just a number, integer, right? And for cons constructor, cons is just a cell, right? It's a box which points to something else, right? So the way it is implemented is, remember I mentioned this something about metadata. There is some metadata that is sitting somewhere. So OCaml sort of says, okay, it pattern matches using this metadata that is sitting on the outside. So when the metadata information says 0, it knows it is nil. So it is just going to do bit comparison. So if the bit is 0, then it is a nil constructor. If the bit is 1, then it knows that this is a cons value. So the first word will be a pointer to the whatever value that is in cons. So this is the exact same way that we implement every OCaml data type. So if you have a particular data type with 7 different constructors, all of which are say nullary constructor, and 3 different constructors which are going to be boxed values, say 7 of 8 of something, 9 of something, and 10 of something. Those are the constructor names. So each of these are compiled to indices. So 0 will be 0 index, 1 will be 1 index. These will just be bit pattern 0, 1, 2, 3. So when you do pattern matching, OCaml is just going to take the value that you have. It knows something about how these things are compiled. So when you pattern match to say 3, it is just going to check whether the value there is going to be just the bit pattern for 3, 0, say 1, 1 in binary, right? And if it is so, it just knows that that value is the third constructor. If it is say 7 or 8, it knows that by at compile time it knows that these are boxed values. These are values that point to other values. So then it knows that the first value is going to be pointing to some object in memory, and then it follows it. So if you want more information on this, I would suggest looking at the real world OCaml chapter. Again, I'm not going to ask you anything about the memory model and so on unless I teach it, right? So, but I'm not teaching it right now. I'll just add you a link. It's a really nice chapter. Actually, it is one of the reasons why OCaml is sort of very easy to compile to. Um, I can't find the link to the book right now. Let me see. So there is a at this point, you have all the information for knowing about reading this chapter. So I've just pasted the chapter description there. Again, no need to study this if you don't want to, but it's a really interesting way of compiling this. So this memory representation is in fact the primary reason why OCaml sort of came into the scene. So so CAML stands for Categorical Abstract Machine. Okay, so machine language. So we don't use this term anymore. But Xavier Leva, who implemented the original OCaml language, came up with this very cool way of making functional programs run very, very fast. Right, and the primary innovation there is this memory representation. It used to be the case that functional programming languages were really interesting, like all of the lambda calculus things that we studied, but we didn't have good methods of compiling them very efficiently until we had this memory representation, which Xavier Leva came up with, and that made the compilation much faster, and that made functional programming very practical. Of course, there are other ways to compile this as well. But this is one of the key results of how functional programming became practical. Anyway, okay, so that's a lot of digression. So Sarthak has a question, which is a follow-up of the arrays question. Each entry is a cell, right? Yes, it is a cell. So can we have multiple types in an array? You cannot have multiple types in an array because every array is monotype, right? So when you declare an array, its type will be some alpha, right? But the alpha is unified with a single type. If you have different values at different types at different indices, then the result of reading the array, right, changes with index. And this is not something that OCaml type system can do. In particular, the type of the result is dependent on the actual value of the index, and these are known as dependent types. And we don't have dependent types in OCaml. Neither do we have dependent types in Java, right? Just like Java, where every array has a single typed value in it. So we have a similar story in OCaml. Okay, so I think I've answered both of those questions. Further questions? I'm going to sit here like in this awkward silence, right? I can just do that. So I think you should certainly ask more questions. Let me ask you a simpler one, right? So, so far, right, what is it that you found difficult about OCaml? Or this course, right? So far, we've seen OCaml, but also lambda calculus. What is it that you find difficult so that we can sort of improve upon it, right? Debugging. Okay, wonderful. Yeah, that's that's a thing that we always have an issue with. So is it, let me ask you, let me try to define it. Is it debugging the type errors or debugging your running program? Abhishek. Like we aren't able to print statements. You're not able to print values, is it? Is that what you're asking? You can add print statements, Abhishek. So you can add print statements everywhere. So you can do printf debugging just like you do in C. Let me try to see whether mm, yeah, okay. So let me try to do this. What I'll do is I'll share my screen so that I can type something. Hmm. So of course, this is very subjective, right? So your actual thing may vary, but I just want to show you that you can do printf debugging. So, so I just have an empty cell, right? So let's say I'm writing a Fibonacci function. If n less than 2, then fib of then 1. Oops. Uh, it's not marked on this code. Okay. So if n less than 2, then I don't know why this is causing so much problem. Sliding. Okay. Okay. Then 1 else fib of n minus 1 plus fib of n minus 2. I need a rect. Okay. So, okay. So I have this function. I just need to know where the control flow is going. So let me um, just do fib of 10 here, right? I get 89, but I want to see exactly how my function is proceeding, right? So let's make it a little bit better. So I want to see what is the actual control flow here. So let me so these are just expressions, right? Let v1 equals fib of n1 and let v2 equals fib of n2 n v1 plus v2, right? This is the same as uh, it's not a function. What is it? What is the problem here? Odd. Oh, okay. I know what to say. So this is the same as what I had earlier. Okay. So I want to see how the control flow is proceeding. So I can do, let's say I want to just print a message at the start of the entry to the function. So I can do printf fib entry %d, right? \n. You need %bang, right? Just so that we flush things out to the standard output. So this is just necessary for the Jupyter notebooks because of this control flow. Sorry, the interaction between OCaml parts and the JavaScript parts that is driving this page. But anyway, so I'm going to print n here at entry, right? Now you see fib entry 10, 9, 8, and actually it goes on for a long while, right? We make it smaller. So it starts with 5, then 4, 3, 2, 1, 0, right? And then it calls fib entry 1, 2, 3, 1, 0, and so on. Why is it calling this way? Let's add a printf here. Um, fib recursive call 1 is %d \n %bar. Say do something before, right? And for n, let's just do n minus 1, right? And you can do the same thing here, right? After fib I call 1, and I want to print, say, fib of percentage d is percentage d. What do I have? Something like this, right? Type unit, but an expression is required of type in which one? 95. This is necessary because you need this. Yeah, now you see you can get more information, right? First, the program entered here, then it printed fib entry 5. Then before recursive call 1, this recursive call, it is going to call that with 4. Then actually what happens is it doesn't return, right? Because of the recursive call, you get fib entry 4, right? It goes through, and then you have fib recursive call 3, 2, 1, so on. So it keeps on going all the way down here, and then it goes to after fib call, right? It eventually gets to 1, and then it is fib entry 1. At this point, it pops out of here, and after this, it pops out there. So you can do printf debugging just like what you do with C. You don't have a step through thing. We don't have an IDE which where you can step through. But I think yeah. So does that help you? Give you some idea of how to debug, Abhishek? This is what I do. Actually, there are other tools. I didn't want to introduce lots of tools in this course. Okay, so yeah, good point. So flushing is it's just an odd thing. So we need this percentage bank. I think I mentioned this in 1 or 2 lectures, but if you don't do percentage bank, it won't print out. That's an unfortunate thing of this integration. So it is not printing out, but if you say just flush this thing, it will keep printing out stuff that was not flushed earlier. Anyway, so good opportunity to repeat the same thing. So yeah, is OCaml compiled to C? Good question. So it's not compiled to C. So the way we have a compiler that I think I can show you this. So this book is sort of really good. I recommend browsing through this book for all of your questions. It's written in a really nice way. Let's see. So the way OCaml is compiled, there used to be this figure here. Thought I had a figure. Anyway, not important. I thought there was a figure here. The way OCaml is compiled is there are 2 compilers for OCaml. There is the bytecode compiler and the native code compiler. Bytecode compiler, as the name suggests, right? Just like Java emits bytecode, and the bytecode is interpreted. And that is what we are actually using whenever we execute programs here. All of our programs get interpreted here. But OCaml has native code compiler as well. And what it does is it goes into some intermediate passes, and then it emits native code directly, just like what you're studying in the compilers course. So it can emit, it supports multiple backends. It can emit to your x86 architecture, but it also has backends for ARM64, RISC-V, which is this up and coming open source ISA, right? Which I think you must be studying for the OS course. It's a really interesting architecture. It's like completely open. We can compile to Power architecture, which is this IBM's platform. It's not compiled to C. It's compiled directly to native code for performance reasons. And compiling to C is always not the best target for functional programs, because C doesn't have anything that is suitable for representing, say, higher order functions. So it is much easier to compile directly rather than compiling through C.
Sir?
Yeah.
Sir, I wanted to ask something about modular programming.
Yeah.
So in when we have modules, like when we have functor, if I want to take two modules as the arguments,
Yeah.
and like they are of actually the same type,
Mm.
but then I'm like inside the body of the functor, if I
Mm.
want to have something like if a particular field value of
Mm.
the first module is
Mm.
equal to, let's suppose, 1, then
Mm.
I want to return the first functor, the first module, else I want to return the second module. Will this
Okay.
and I have typecasted them both to some t, and
Mm.
both involve abstract data types. So
Okay.
that will create a problem for me in OCaml, or like.
I think you can do it. Let me try to write it down. So let's define module type T. You need to tell me whether I'm going in the right direction. So if I understand your question right, so we have a module type T, right, which is sig. And what do you have here? You have an abstract type T.
Yes, sir.
Okay. And then you also said value is something, right?
Yes, sir. Some v equal to 10, let's suppose.
Integer, right?
Yeah.
So, okay. And then, uh,
And I have two
yeah,
modules which are of this type only.
yeah, x say t, and then y say t. Okay. Then what do we do?
Sir, then like once I have these two in this functor, like how will OCaml know that these two x and y have the same abstract data type? Like, do I have to specifically write like we wrote for like t with t dot t equal to x dot t, something like that?
So one thing you can't do is you cannot. You, right. So let me. So we have two modules. We have two modules of the same type. So the question is whether you can do this, right? So you can certainly ask whether x dot u is one. So so this expression has type int, but an expression was x dot p. Oh, sorry. We can ask whether this is true. This is fine, right? Because we know that v is going to be integer.
Sir,
Yeah.
like what I meant was like if I have these two x and y, like
Yeah.
can I have an if statement which returns one type of structure if x dot t is like some given value, like some condition I have, and like I have an outer if statement. Is that
Yeah. Yeah.
possible?
Yeah.
Like
No.
two
So good
types of.
question. So you cannot. So okay, really good question. So you cannot do that with the facilities that we've seen. So what you're saying is, I want to essentially have a if statement, which is this term language, right? Execute the program, and based on that, return one of the structures. Is it? You want to actually
Yes, sir.
return?
Like at compile time, like we won't know
Yeah, yeah. You
beforehand, but
can't.
in time we'll decide.
You can't do that because the modules are all resolved at compile time, right? And the if statement, the semantics of the if statement is described at runtime. So you cannot do that. There are features in OCaml with which you can do it, but we are not. We haven't studied that. In particular, first class modules is what allows you to do it. All of the module language is resolved at compile time, right? All of the term language is at runtime. So if and while and all of these things, right? They're all at runtime. So based on an if statement, you cannot return two different modules. Is that
Okay, sir.
okay?
Yes, sir. Understood.
Yeah. This is just like C++ templates, right? C++ templates are all resolved at compile time. They have nothing to do with runtime structures. So similarly, all of these things are resolved at compile time. Okay, so good question. Any other questions? Let's continue from what I asked, right? So debugging was certainly one thing that Abhishek said was difficult, and you can do printf debugging. That's not the best thing that you want to do, but I think that just works. What else did you find difficult? Um, Writing OCaml and reading the code and the lectures and so on. So is there something else that you particularly found difficult to do or difficult to follow? The assignments are all okay, reasonably paced, right? So far, there were 2 assignments only so far, and I've released the third one. Yeah, you can answer with an yes or no. Okay. Yeah. So thanks. So the way I look at assignments is they are a way for you to learn some additional concepts as well, and this will be the structure that we follow for the rest of the assignments, right? So you won't need anything other than what you've learned in class to do the assignments, but you'll need to apply it, right? So it won't directly be, if you know if you sat through the course lectures, you won't be directly able to do it. You will have to apply the knowledge, right? So I will I'll try to bring in like 2 or 3 concepts together in the assignments. This might not have been covered in the lectures themselves, but I think you should have all of the um, tools necessary to do the assignments, right? But the assignments themselves are laid out in a way that they are going to teach you one concept at a time. And hopefully the test cases that sit directly below the assignments, each of the problems should help you get there. There are hidden test cases, right? I think a few of the students have raised a question regarding why they haven't got 100% marks in assignments. We have hidden test cases. The plan is to share the hidden test cases with you. So we will just figure out how best to do it. One thing I would like you to still follow is make sure that when you submit your notebooks, you use your roll number as the file name. That makes it easier for us. Otherwise, we have to do other things. But if you make sure that it is just the roll number .iponb, then everything should be fine. Okay. Any other comments, questions, anything at all? Okay, so in that case, what I'll do is I'll just start the next lecture. I don't want to waste your time as well. So we have 15 more minutes. So I'll just start up the next lecture and then we'll continue tomorrow. Um, so we've done modular programming. The next thing we are going to do is streams. Okay, so let me close this. I can't close it. Why? So this lecture is going to be sort of a collection of ideas, right? So I wouldn't put them in a single basket, but the way this lecture is organized is there are a few interrelated ideas which we are going to combine it in the context of a single lecture, right? In particular, we are going to look at streaming programming. We are also going to look at lazy valuation. Lazy valuation ties back to one of our reduction strategies, right? Where we saw call by need, and OCaml has lazy features built in. So we are going to look at lazy valuation, and we are also going to look at memoization. Memoization is the concept of storing intermediate results, right? Storing pre-computed results. The concept is closely tied to dynamic programming, right? In dynamic programming, that's what you do, right? You build a table of the previous results so that you can reuse it. All of these are somewhat related, and this lecture sort of lays them out in a way that um, I have an easy segue between each one of those. So the question is, why do you even want to study streaming programming and so on? If you work in, say, distributed systems, right? If you go to the industry and then start working on any real software that combines multiple microservices. Today, everything is deployed as independent services, right? So let's say I have a Twitter. I am Twitter, and um, I want to do some recommendations or analysis, or I want to show what are the trending topics currently in a particular location, say. So the way I would do it is there are multiple users who are all posting tweets at the same time. There are like thousands and hundreds of thousands, millions of users who are posting tweets, right? And the tweets are constantly coming through, right? You can sort of think about the tweets as a stream. Essentially, it's like a tap, right? If you open the tap, the tweets keep coming in. And I want to show you, my problem might be, say, I want to show you what is the trending topic in India, right? And this might be some topic. I don't want to pick any particular one, but uh, I am going to pick the trending topic based on a geographic location, right? The trending topic in India might be very different from the trending topic in, say, the USA, right? So there is a stream of tweets coming in, and let's say the stream includes all the tweets that are produced by all the users across the world. What you need to do for first thing that you need to do for computing the trending topics in India is you want to filter out those topics which are uh, not from India, right? Those tweets which are not from India. So you take this tab, right? You put a filter on it so that it filters out everything that is not from India. And then the thing that comes out is also like a stream, right? It's also a stream which only contains tweets from India. And then what you do is then you look at the hashtags, right? You look at the hashtags, you take a period of time. This might be, say, um, takes this is not a precise algorithm, but take um, like a minute, right? Collect all the tweets that are posted in the last minute, right? Compute the counts for each of the hashtags, and the maximum frequency is the trending topic, for example, right? So what does it do? It first filters it out, and then it sort of applies an operation that works on a segment of the stream, right? So it is and it's a continuous operation. So this is not going to be just some 1 minute. You have to keep doing it for every minute, right? And this is also a stream, but a stream which is sort of much more infrequent. So you get a frequent topic every minute, but it's still a stream. So what is happening here? One way to look at this is there is a stream of things that are flowing through, and there are transformers, right? The first transformer filters out all the tweets that come from anywhere across the world. The only thing that comes out is Indian tweets. And then the next transformer sort of spits out, right? Every minute, what are the trending topics? This is essentially stream programming, right? You have a stream and you have some functions that you apply which manipulate the stream and produce a new result. Except unlike what we've seen so far, these streams are infinite, right? And these functions are just, you can imagine them to be pure functions. So the filter is just a pure function, which doesn't have any state. It knows something about India, but that's not a state. And it spits out another stream. And there are real frameworks in the industry, something like Kafka, Apache Kafka, and all of these other streaming frameworks, which allow you to do functional programming over stream. They don't call it functional programming, but the hope in this lecture is that you will sort of pick up ideas, right, which you can see in these real frameworks. And they all have certain operators which are common, and we will sort of see them in the context of OCaml. So we are not going to see Apache, Kafka, and so on, but we will study them in the concept of OCaml. So that's the setting for this lecture. So let's see what they are. So what I will do is I'll clear my output so that I don't give away surprises. Okay. So one thing that OCaml allows you to do is, just like we defined recursive functions, it allows you to do define recursive values. This seems quite strange at first, but let's just keep going with it, right? So here is a recursive value, which says it's a letrec, right? It's a recursive value, and the name is ones, and all it does is it creates a list, right? With the head is one, and the tail is the same thing that you're defining. And it's like this cycle that you create. So there is, the list has one as the head, and the tail is the thing that you are actually defining. So what you end up defining is a infinite list, right? Because these are just cyclic. You have an infinite stream of ones here. So you can ask for the head of this list, you'll get one. The tail of this list will be the same stream, right? And here is an infinite stream, right, which is 0, 1, 0, 1, repeating so on. So it's a letrec, right? I name it 0 ones. The first element is 0, the second is 1, and the rest of the list is the same as the one that you're defining. So it is going to be 0, 1, 0, 1, 0, 1, and so on. So the list itself is infinite, right? If you start looking at, say, the millionth element, you can ask for the millionth element, but it uses finite memory. It's basically a cyclic list, and that is the actual way it is implemented. So this list has one box which is 0, which points to the next box which is 1, and the tail of it just points to the first element, right? Okay, and that's why you see 0, 1, and then cycle just says it's pointing to something cyclic, and here it just points to 0 ones. Okay, so I think I've sort of given you the practical motivations for this. Can I sum the values? That is precisely what we are going to see. Sarthak is asking, can I use some values if I want an infinite binary string? Give options of both 1 and 0. So what we are going to see in this rest of the lecture is how do you actually manipulate these things, right? A naive way does not work for obvious reasons, but we will sort of look at how to make it actually work. So I gave you one motivation for streams, which is this distributed systems, right? And this Twitter trending topics analysis. But there are also a lot of other topics. In particular, you can define infinite sequence of primes and Fibonacci numbers in an interesting fashion that tells you about the structure of these primes and Fibonacci numbers. And all of these operating system abstractions, right, which are sockets and file descriptors, they're all streams. So when you say I open a socket on Unix, you sort of look at the socket as a stream which has multiple packets flowing in, and you can wait for inputs on this stream and act upon it. You can say, okay, I got a packet and I'm going to process this packet and send it through, but I'm also going to wait for the subsequent packet. That also is a streaming interface. And these infinite data structures also appear frequently in games. So imagine Pac-Man, right? In Pac-Man, the ghost can chase the Pac-Man around, right? around a cyclic path. So if you sort of imagine every state of the board of the screen as a state, and then whenever you make a move, it is one option, right? You can either move left, right, up, down, and all of these different ghosts can move in one direction. So it creates from a given state there are multiple outward next states, and I mean this is a tree, but also the fact that you can keep looping around, right, means that there are cycles in the tree as well. So the game trees in real games are tend to be infinite, and you want to say something about manipulating these game trees in an interesting fashion, and they are also infinite data structures, right? So these appear in multiple places. So the limitations of cyclic structures that we've defined so far in OCaml, right? Suppose we want to convert this infinite list of 0 ones to string. Can I just do the obvious thing that I will do when I have a list, right? How do you convert a list of integers to a list of strings? You take the string of int function, which takes an integer and then returns your string, and then you map it over the list, right? You map it over the list so that you get a list of strings as an output. But this won't work on 0 ones. Why? If I do this, I will get into this infinite execution, right? And I stack overflowed, and OCaml says there is a looping recursion because what does list.map do, right? List.map goes to the first element, applies this function, string of int. Oh, I got the string, and goes to the second element, applies this function. That's fine, and then it keeps on going this way, right? But the list itself is infinite. So you are going to end up with this unfortunate place where you want to do interesting things to manipulate the stream, but the obvious way of doing it does not work. So if you just do the standard list.map on this infinite stream, it stack overflows. And the question you want to ask is, does that mean that we cannot manipulate these streams in any interesting fashion? That's not the case. So here is one way of starting off, right? So what is a list? A list is a type, right? It's a polymorphic argument. So it's a polymorphic list with the nil constructor and a cons, which constructs a node, which has a value and the rest of the list. Okay, so the list is either empty or it's a cons where you have a value and the rest of the list. We can sort of take this type definition and make it into a stream, right? As I mentioned, the stream is infinite, so there is no nil. So there is no end to a stream. So here is a definition of a stream. So a stream is an alpha stream, which only has cons. So it has a value and then the rest of the stream. Okay. So this still doesn't work. I will get to why. So here is the construction of infinite stream. So it has a 0, 1, and 0 ones, right? Cons 0, that's the first element. Cons 1, the second element, and the rest of the stream is just the 0 ones here. Okay, so I can define this. This will be an integer stream which has a cycle. So this particular position points back to the 0, 1 stream. I have a toString. The way I define toString is give me a stream element which I know that it's a cons. The only constructor is cons, right? I can pattern match it exactly using one pattern. So I happen to pattern match it at the argument position of the function, right? Cons has a element head and a tail. So when I want to convert the entire stream to a string, I first apply string of int to the head, right? So I get a string here, and I recursively call toString on the tail, right? Obviously, this doesn't work. I just want to show that it doesn't work. And I construct a stream again. The type checking works, right? The types are fine. So we are not actually running this. So it says, oh, you have an int stream, that's fine. This function, if you are able to run it successfully, will give you a string stream because I converted this integer to a string. But when I actually apply it, I get the same problem. I get this stack overflow because the stream never ends, right? So what is the problem there? The problem there is whenever I go to a tail, right, I shouldn't keep on going. I should probably stop here, right? I should do this operation. I should suspend the computation here. I shouldn't eagerly go and evaluate everything there. I should probably stop there unless it is required, right? And I'll stop here. So there is a nice trick where we know how to suspend a computation. That's the trick that we will see tomorrow. Okay, so we will continue with that tomorrow. Thank you.